Good evening to Dr. Ujila, and I'm Kirubana Vasu. And my other group mates for this group video assignment is actually one Faris, Salman, and also Zhang. So they will be appearing in other scenes of this video. So now today I'm the representative of my group mate to start the introduction for heat conduction. What is heat conduction? Actually, heat conduction is also given with another name, which is heat diffusion. What are those? Actually, heat diffusion is simply that hot particles which will be diffused into a colder region from a hotter region. So basically this is a scientific term which we are not going to discuss in this video, but we are going to discuss on the mathematical proof. How can we prove this heat conduction? Through mathematically using partial differential equation, which is known as also PDE. So over here, when you come and have a look over here, as a result of heat conduction heat, this is actually a hot water vapor had been touching the cold surface, which leads to condensation. This shows the heat diffusion. It occurs from the hot water up to the hot air particles up to the cold surface. And that's all from me.
Good evening, doctor. I'm Zhang Xiaojian. My lecture number is ES02139. And today I will use the exam and slow this exam. For this exam, I will use this way. So we are assume lambda, and so not equal to 0. So is close the final answer. N equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can equal the final answer. N equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. So that's all.
Assalamualaikum. My name is Salman bin Muhammad Salim, metric number 1948894. So today I will be presenting about partial differential equations and why we need to assume the values of lambda in order to get an actual solution. So in order to solve our partial differential equation on the heat equation, we need to assume values of lambda first, if not we can't get any solution. So the first step, we can actually assume three different values of lambda. The first one, if we assume that lambda is greater than 0, we will get this solution, which is phi x equals to c1 cosine square root of lambda x plus c2 sine square root lambda x. So that would be if we assume lambda is greater than 0. Now second, if we assume lambda is equal to 0, we get a shorter solution, which is phi x equals to c1 plus c2x. So now the third and final one, if we assume lambda would be less than 0, we get this, which is phi x equals to c1 hyperbolic function here cos h square root of negative lambda x plus c2 another hyperbolic function sin h square root of negative lambda x.
Okay, so for now I will continue what Salman already explained from the previous step. So for my step, I will continue from lambda equals to 0. So now let's solve for the time differential equation. For the time differential equation, we have this equation, which is dg over dt is equals to negative k lambda kg. And note that even though we now know lambda, we're not going to plug it in quite yet to keep the mass to a minimum. We will however now use lambda to remind us that we actually have an infinite number of possible values here. This is a simple linear and separable, for that matter, first order differential equation, and so we'll let you verify that the solution is g t is equals to ce minus k lambda nt is equals to ce minus k n pi over l squared t. And then after that, we will know that we've gotten both of the ordinary differential equation solved. We can finally write down a solution. However, that we have in fact found infinitely many solutions, since there are infinitely many solutions. As an example, eigenfunction to the spatial problem. Our product solutions are then is u and xt is equals to bx sin n pi x over l e negative k n pi over l squared t, and the n value is equals to 1, 2, 3 and so on. So after that, we've denoted that the product solution u to acknowledge that each value of n will yield a different solution. Also note that we've changed the c in the solution to the time problem to b, to denote that the fact that it will probably be different for each value of n as well, and because we kept the c2 with the eigenfunction, we have absorbed it into c to get a single constant in our solution. Our group, I hope you will give our group a good mark. Thank you, Doctor.